Hello class, in this session I'd like to walk you through the parts that make up power and distribution transformers. So when you're talking about power transformers and distribution transformers, you're not talking about the small ones, you're talking about the big ones that you would see in your city, in your towns, close to railway stations, the ones that transfer power from one city to another city, from the power generation unit to your load, which could be your home, kilometers away. So how do these transformers do it? We know we talked about step up and step down, but at this session we're going to talk about the parts that make up these transformers. These transformers are bulky and they are efficient when they are perfectly cool and operated within the rated specification. So when you're talking about operating within the rated specification, it is all about having it operate within at highest efficiency. So what are the parts you've observed in the transformer in your locality? When you see a transformer on a pole in your locality, when you have 11 kV line coming into the college or to your village and it's being distributed, you would see a small transformer there. What are the parts that you have observed in the transformer? Let's see that in detail and know exactly what are those parts. So there are some parts you can't see externally, but I would like to list it out as parts, but I would like to go through the entire list. So you have your insulating material. So the first insulating material that you would see externally would be your ceramic insulators or your glass insulators, which would be those stacked up layers of ceramic discs, which would be your insulator to prevent your high voltage from making a contact with any other metal or grounded part or coming in contact with the secondary. So that's your insulating material, which is what you normally see. Besides this, the most critical insulating material that you have in these transformers is transformer oil. Transformer oil does play the part of insulating the coils that are inside the transformer. At the same time, it also does the work of cooling the transformer. So we'll talk about cooling in detail. Second is windings. We talked about primary winding, secondary winding, turns in primary, turns in secondary, the voltage and currents in primary and secondary. That's what windings are all about. Next is your laminated core. We talked about transformers need to have a core to have the flux flow with least reluctance. That would be your transformer core. It's normally laminated so that you don't have currents losses due to eddy currents inside the transformer laminated cores. Then you have a tap changer. Some transformers have tap changers where the number of turns in your primary or secondary can be altered using multiple taps to be able to get voltage regulated voltage on your secondary. And the second most important thing we talked about is transformer oil. Yes, it's a mineral oil extracted from crude oil, which is used in transformers to insulate them, cool them, and keep them well in working order. Cooling tubes. Cooling tubes are just the radiative fins of your transformer to keep the oil inside the transformer cool. So the moment the oil comes in contact with the transformer and it becomes hot, its density reduces, it rises up to the surface, goes through these cooling tubes, radiates the heat into the atmospheric air, and sinks back to the bottom, and the circulation of oil is through these cooling tubes. Explosion vent. Explosions in transformers are possible. We don't want the entire transformer breaking up. In that case, you have a small vent that explodes, which is the weakest part of your transformer, which explodes to say that there's a fault inside the transformer. Your breather, yes, transformers do breathe, which is when the oil expands, air is expelled, and when the oil is cooled down, it breathes in air when the oil contracts. And that air goes through a breather to prevent moisture from coming in contact with the oil inside the transformer. Oil conservator is a place where your transformer oil has place to expand and contract, which is where the air is expelled out or drawn in through the breather. Then you have the last one is a Buchholz relay, which is a relay which acts as a safety device for the transformer in case there's a fault to turn off the transformer or cause an alarm. Let's look at it in detail. So the most critical part we talked about transformers, the ones that we see in our villages, which is the distribution transformer. We have a 3-phase 11 kV line, and you have a 4-tapped 440 volt secondary, which is distributed throughout the city. Now, in case you don't cool the transformer, if there's a fault, you would have an explosion, and it's filled with oil and is flammable at high temperature. So it's important to control the temperature of your transformer within permissible limits to prevent the transformer parts from degrading and the insulation breaking down to cause an electrical fire. And There are some cooling systems installed in transformers. Sometimes you even have pipes with cold water to keep the transformer cool in case there is an emergency. So the most important thing, if it heats up and dissipate the heat into the atmosphere, keep it cool, you would have long running conditions. Now the functions of the individual parts of the transformer, we'll study them in detail. So we're going to analyze only the physical parts. We're not talking about the inner working. We're not talking about the flux. We're not talking about the workings. We're talking about the physical parts and how they work in the transformer in this session. So the insulating material. We did talk about the ceramic insulators. We do have many other insulating materials. We talked about oil as an insulator. We do have insulation paper. We have insulation tape. We have press boards, wood laminates, plastic, glass, ceramic, and oil-based varnish for certain parts. Now, talking about insulation paper, when I have two windings close to each other, I put an insulation paper in between. If I want to have the windings held together, I bind it up with the tape. If I want to hold windings and space them up from each other, I put press boards in between. If I want to hold the conductors, the incoming and outgoing lines of the transformer windings, then I use wood or wood-based laminates to hold them in place. There are some plastic parts for transformers, like high-grade, the ones that have high insulation resistance, you can use plastic. There's glass when you have, or ceramics when you have the high voltage or low voltage line entering through the transformer body or leaving the transformer body, you have glass or ceramic insulation. Then you have oil-based varnish to prevent metal parts that are coming in contact from rusting or degrading electrolytically or due to decomposition, and to prevent voltages from leaking through metal. So you prevent it or preserve it from moisture by using oil-based varnish. So the most important insulating material we talked about is the oil, and it's most commonly seen in voltages of 11 kV and higher. You don't see them in lower voltages most commonly. So you talk about a simple auto transformer is air cooled. A simple transformer used in an appliance is air cooled. When talking about 11 kV and high kV rating or MVA rating, you would see auto transformers that have oil as their coolant and used to require to dissipate the heat in such transformers. So, and if the oil goes bad, you can have the oil filtered and reused back in transformers. And how do you test the quality of the oil? We do have an instrument called the oil test kit. You see one in our lab too. We apply high voltage between two spherical electrodes or electrodes that are in close proximity inside the oil. When the oil breaks down, you would see a spark, and that voltage at which it breaks down is your breakdown voltage. So you need to have a really good high voltage so that it doesn't break down when you have the voltage between turns exceed a particular value, or between your primary and secondary, especially when you have concentric winding in your transformer. Next is your insulation class. All transformers don't have oil, and all transformers don't work at the same temperature. When you use cotton and silk as your insulating material to hold your transformer in place, when it gets hot and the temperatures exceed 105 degrees, your cotton and your silk start deteriorating, and you would get carbon dioxide gas, and the whole thing would break apart. So when you look at a machine, any machine, in the nameplate you talk about class ratings for insulation. When I look at a rating and it says class F, what does it mean? It can withstand a temperature of 155 degrees on a single spot, and the insulation is mostly glass, mica, asbestos, or with suitable binding materials impregnated with varnish or any coated substance, plastic based varnish or coated impregnation. So that it's this class F. The moment I see class F, it's suitable for temperatures as high as 155, and that's how I identify what type of material is used in the insulation and what temperature can it withstand. The most important thing in windings of transformers is to understand how it's assembled. You talked about wood-based laminates. So you have wood-based laminates to hold these multiple terminals for your primary and secondary. So you have multiple sets of windings. You have different stacks. In other words, when you have the windings manufactured, they manufacture as stacks, and they stacked up together to identify the turns for primary and secondary. If it's going to be multiple taps on your primary or secondary, those taps would change the number of stacks on your primary and secondary to be able to get your desired voltage on primary and secondary. So the design factors that go into the transformer talk about how the transformer is being manufactured or constructed. That's the design phase. So this is your wood insulation. The entire structure is going to be immersed in oil. That's more important. So you could have your primary on the inside, secondary on the outside, where you have a bobbin to hold the winding in place. Then you also have your magnetic core where your flux flows through. Then you have your enclosure which has oil filled in to keep the whole structure cool. Now, talking about the transformer core, we talked about the laminates. The transformer core is made out of not a single piece of metal, it's multiple laminates, so that the flux does not have any current that's being induced into the soft iron core. We talked about flux and we talked about Fleming's left-hand rule, right-hand rule, talking about the EMF equation. We say that the flux and the current are perpendicular to each other. So when a flux flows through the core, perpendicular to it, there is a current that has a tendency to flow. I don't want that current to flow. The more current, those currents are eddy currents, and the more they flow, the losses are higher, the core gets hot, you have a resistance path created for the flux, and so for the current, and that is your soft iron core. Is not a big perfect conductor. Instead, you split them up into laminates. These laminates are insulated from each other with oil in between, varnish in between, and these laminated cores do a good job in having the flux pass through, but no currents, eddy currents flowing within them, thereby improving the efficiency of your transformer. The next topic will be tap changers. When you talk about tap changers, there are two things to remember. One is called an on-load tap changer, another one is called an off-load or a de-energized tap changer. So the advantage of having a tap changer is I can change the number of turns in my primary or secondary to get a desirable voltage in my secondary or primary, and to be able to control the turns ratio between primary and secondary. And this can be done on the fly. In other words, when the machine is on and running, you can even change the number of taps, the number of turns, by using a sliding tap changer to be able to change it. There are some machines that needs to be de-energized before you use the tap changer. In those cases, you have a de-energized tap changer. So this is a simple, typical diagram of your high voltage tap changer on your primary to be able to get the desirable voltage on your secondary. For example, if you're supposed to get 11 kV and you just got 10.9 kV, you want to increase the voltage, you can change you can reduce the number of taps, windings on your primary to be able to get the higher voltage on your secondary. So this is how your tap changer works in transformers. The next thing is cooling tubes. So the most important thing in cooling tubes is understanding why cooling is what happens in the cooling oil. When the cooling oil comes in contact with your winding, it gets hot. When it gets hot, it expands on heating. When it expands, its density reduces. When its density reduces, it becomes light. It moves up to the top of the tank. When it moves up to the top of the tank and it moves out into the radiator tubes, here you have oil that is being exposed to the air, cools down, contracts, becomes heavy, goes down to the bottom. So there's a circulation of oil. It's called a convection current, where it's heated up here and cools out here. And these fans are not always running. When the temperature of oil exceeds a particular value, I can have forced air flow over these ventilator fins to cool down the oil. Most times in smaller transformers, just have ventilator fins like radiator oil tubes, which don't have fans to cool them down. So it's natural convection of current into the surrounding air to keep your air transformer cool within operating conditions. So this is the forced or the natural way of cooling a transformer. You would have seen them in practical. These are the breakdown to say exactly what do these fans do in bigger transformers when you have a distribution yard. So this is a simple distribution transformer. Let's look at the different parts that you might not see normally in diagrams. The first thing is your explosion vent. In case there's a fault inside the transformer, there's a big surge in the gas that's being released by the transformer oil, and that would cause this explosion vent to explode, spilling out the transformer oil from inside it. So this transformer oil could be hot, so it's not a safe place to stay, especially when your transformer is having a fault and this transformer vent explodes. So that's one thing. Next thing I want you to notice, there are 3 high voltage terminals, which is the 11 kV line, and then you have the 4 terminals here, which is your low voltage side or LV side, which is 4 terminals. How come 3 to 4? This 3 means it's delta connected. When there's 3 terminals, it's a delta connected connection. So there's turns, first coil set between 1 and 2, 2 and 3, and 3 and 1. So this is your delta connected primary winding. This is your star connected secondary winding, which has a neutral also. So this is why you have 4 terminals on your out secondary and 3 terminals on your primary. Then you also have your oil temperature gauges, you also have your conservator and other parts. We'll look at them in detail. So the most important thing you need to understand about the explosion vent, it's the weakest point in the transformer body. There's high pressure breakout. Air can slowly be vented out through the breather. The explosion vent explodes and lets the oil spill out and regulates the pressure, preventing the entire unit from exploding. Next is the breather. Transformers do breathe. When I say breathe, during the day you have high loads for the transformer, where the transformer oil inside the transformer heats up and expands on heating. When it expands on heating, the oil inside the transformer through a tube goes through the Buchholz relay and goes into the conservator. So the oil rises inside the conservator. When the oil rises inside the conservator, the little air gap or the air pocket inside the conservator vents out the gas through the breather into the atmosphere. When the evening, when the loads are reduced, the factory is shut down, the loads reduce, the transformer cools down, and when it cools down, the oil contracts. When the oil contracts, the oil in the conservator drops down to create a low pressure. When the low pressure is created, air from the atmosphere goes into the conservator. When the air goes in, I don't want any moisture entering the conservator. To prevent moisture from reaching the conservator, because moisture, water is a very bad enemy for transformer oil, I have a silica gel filled in the breather. So the moisture in the air is absorbed by the silica gel, only the dry air enters the conservator. When the conservator is cool, the oil is, as a low pressure created here, air goes in, pressure is regulated back inside your transformer. So this absorption of air and expulsion of air goes through the breather. This is a normal process, and this is why a breather is required to prevent moisture from entering your transformer. Next is your oil conservator. As I said, when the oil expands, it needs a tank to expand and contract. So there's a little air pocket to make change for this expansion and contraction. It also acts like a reservoir. In other words, I want to know how much oil is there in the transformer. I see as a seeing glass here. I can see the level of oil inside the transformer. If I want to top it up, I can open it and top it up during my scheduled maintenance. Next is the important part would be a Buchholz relay. Now, looking at the Buchholz relay, it's connected between your transformer and your conservator. So what happens is, in case there's a fault in the transformer, and normally transformer oil is flowing up, gets heated up because of the winding, gets cooled down through the radiators, goes back in, again circulates. So this is your normal circulation of oil. If there's a fault, those bubbles that come up to the surface slide in and go through this tube and get trapped in the Buchholz relay. When the number of bubbles in the Buchholz relay gets accumulated beyond a particular value, beyond a particular volume, it trips the float switch in your Buchholz relay to cause an alarm in your control room. In case there's a fault beyond control and the volume of bubbles are too many and the second switch is triggered, the transformer is shut down. So bubbles in transformer oil is undesirable. It only happens during the fault. What happens when you have a fault? These bubbles get accumulated inside the Buchholz relay, and there's a small vent there. You can sample out the gas that's coming out from the transformer, take it to your lab, identify the composition of the gas to see if it's carbon dioxide, you know that's paper insulation or cellulose material that's being decomposed, or if it's wood that's being decomposed, or if it's like gases that are combustible like acetylene, you know that the transformer oil is breaking down. That could cause an explosion. So you know the severity of the fault by analyzing the gases coming out of your Buchholz relay. Now let's look at a cut section to see exactly everything in its place. So you have a thermometer to tell you the temperature of the oil. You have your primary, which is your high voltage line coming in to the transformer. You have a secondary voltage line going out to your secondary terminals, which are the 4 terminals. Your primary is your 3 terminals here. So the entire system is filled with oil through the Buchholz relay all the way to part of the conservator. When it breathes, air goes out and comes back into the conservator. So that only the air going out and coming in is to the conservator. The remaining oil is completely moisture free. Now, when you have a bubble coming out, the bubble goes up into the Buchholz relay. So look at the Buchholz relay. This is what it looks like. These bubbles come in and get trapped and they push the float down. Normally the float is pushed all the way up. The float comes down, it triggers an alarm. Now look at the internal parts here. So you have a float contact, 2 floats. When bubbles start getting trapped here, this oil level goes down, 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 and this bubble becomes much bigger and bigger. The first float would be your alarm trip. The moment the float switch comes down, it trips an alarm, and you get an alarm in the control room. If the bubbles get accumulated even more, it comes to this level, it trips your entire transformer off. Next, you need to understand that this Buchholz relay is connected between your main tank and your conservator. So only the bubbles that come here trip here. If it's a high pressure explosion, your explosion vent would give way. Yes? So this is not talking about high pressure explosion. It's a small bubble that's leaking out between the windings that gets accumulated, that flows up into the tube and gets collected in your Buchholz relay and causes a trip. Now this is your silica gel breather. So when air is need to be sucked in, when this oil gets cooled, air goes in. The silica gel crystals absorb all the moisture in the air. They are blue, which means it's good. If it turns pink, which means it's moist and it can't absorb any more moisture. So the air goes in through the breather and into the transformer body, through the conservator. So this is the only way air can enter and air can exit. So preventing moisture from coming in, but air can breathe in freely. So this is your parts and construction and cut section of your transformer. So this is only, all the parts that you've seen now is only suitable for large form factor, kVA rated and MVA rated transformers. You will not see them in small transformers that are air cooled or where they're forced or natural convection. You always see, example, the one we have in our college is oil cooled and it's a 66 kVA transformer. Those have oil and those are having the same parts. Maybe it does not have a tap changer, but the rest of the parts are more or less the same as you see in this study. So if you have any questions, feel free to contact me with your questions and I'll be able to answer them. So please engage in the class and take up your tests on time so that you study on time, prepare for your future. In other words, you're not preparing for an examination, you're actually preparing for your future, because what you learn now is what you're going to remember when you graduate as an engineer. So good luck with your electrical engineering. So if you have any questions, please do contact me and I'll be able to answer your questions. Thank you and have a great day.